Inverse trig functions. So we just did, our last problem on bell work was the derivative of an arc, sine, tangent, cosecant, whatever, all right? So now what we're doing is we are recognizing that derivative and working back into it, okay? So these are only three I'm going to require you to know: your arc sine, your arc tangent, and your arc secant. You'll notice when you take the antiderivative that you throw in this 1 over a. So if you look at page 383 back here, you don't really have the numbers come into play here like you do for this going backwards. And it's because you have to consider the derivatives then have this potential division problem. And so when we're doing these, and we're going to do some type of U substitution, but not exactly like you're used to. So you'll see it kind of cancel out a little bit more than it does in other U types of substitution. But when you have these three types, you need to recognize them or an alternative of them. All right. And so we're going to do some examples where they're just right in your face. And we're going to do some where you have to kind of finagle for them to be right in your face. Okay. So if you have a number squared minus a function squared under a root, that's going to be your sine. All right. And you need to know the antiderivative of that. It's the function over the number plus c. When you have no root on the bottom and it's just the number squared plus the function squared, that's your tangent. You'll notice you have 1 over the number. Now remember, this is number squared. So if this was 4 plus x squared, your number would be 2 because 2 squared is 4. All right. And you'll see a lot of times roots, like don't think back of algebra days when it has to be a perfect square. 3 plus x squared would work for arctangent because 3 has a root. It's an irrational one, but it's the square root of 3, right? So you still have to think outside of the perfect square box. We're just looking for a number plus a function, all right? And then we're going to take the square root of those. That's tangent. Secant's probably the most difficult to recognize because the example that we do kind of throws it in there and you didn't realize you even had it. But when you have this subtraction of the function first and then the number, and then the function itself on the outside, that is your arc secant. And so that's one that we're going to do as well. So let's look at the first example here, example 1. We have a number minus a function squared. All right, a number minus a function squared. That is my sine. That's my sine. And so I'm going to look at that and I'm going to recognize that as arc sine. And then it's just a matter of plugging it in. If I were to just look at this, I would say, well, my A here, my A is going to be 2 because it's basically 2 squared minus x squared, right? That's what I'm looking at, a number squared and a function squared. So my A is 2 and my U is x. And then I literally just plug it in to my antiderivative. So it's going to be the arc sine of my U, that's my x, over my A, that's my 2, and then of course plus c. We will do some definite integration, but of course with indefinite, I always have that crazy little plus c there. Next one. And there's a difference between B and C, and I'll show you what it is. We're not going to technically use substitution, but you have to think about what happens in your mind here. All right, so for this guy, if I were to write out what I have the square root of 2 squared, right, plus 3x squared. Okay, makes sense? And so I do have to consider, so if I were to rewrite this that way, I would have my dx would include a 3, right? Because I have 3x there. And I have the square root of 2 squared plus the 3x squared, all right? Now, because I have this little 3 up here, what do you think I need to do? Yeah, I need to do a 1/3 out here. Yes, does that make sense?
I don't understand how you have the 3 on top.
So instead of like writing it out to the side, I wrote it here because if you look at your antiderivative, your antiderivative is your du over it. Your du is 3dx, right? But I still have to consider that 3. If you look at your derivatives are u prime over 1 plus whatever squared or whatever. You have your whole, that's part of your derivative that u prime is. And so I'm just showing you what u prime is. It's 3 dx. But I still have to consider I have to get rid of that 3 because it wasn't in my original. Now here, when I do this, so if I just do the antiderivative, so I'm just doing the antiderivative of this. This is the perfect antiderivative of my arctangent. I have my du on top and my number squared plus my u squared. Okay? So that's my perfect arctangent. And so when I actually do that antiderivative, I have a 1/3 that's here. And then the antiderivative of arctangent is up here. So I have 1 over my a being the square root of 2, right? Arctangent of my u, which is my 3x, over my a, which is the square root of 2, right? And I have that plus c. So when I simplify this, I have 1 over 3 square root of 2, arctangent of 3x over square root of 2 plus c. Let's look at this one. All right, so the first thing you're going to notice if you have a function minus a number, okay, a function minus a number. And so you want to establish what is my function. My function is 2x, right? My number is 3, okay? So then I know that I'm looking at secant. And so if I were to rewrite this, my function would be, it would look like this. So I have 2x. My derivative of my function here would be 2. So if I did use substitution, it'd be 2 dx, right? Over, I have my x here, square root of my 2x squared minus my 3 squared. Because I have that 2, I need to multiply this guy by 1/2. Now here's what happens on this guy. On the other guy, I have something plus something, right? So I don't distribute that 1/3 through, all right? And so with this one, because it's all multiplication, you kind of end up with it kind of canceling out there. Like it cancels out because it's multiplied here. It's multiplied, we don't have a grouping around it. All right, if we had a grouping around it, we would have a 3 and a 3 up there. But down on the bottom, it's all multiplied. And so you actually end up with those guys when you take this antiderivative canceling each other out is kind of what happens here. So if you look at the antiderivative of arc secant, we have this 2x counts as my function. So I still have my u prime over my function minus my u squared minus my a squared. So this 2x and 2 is all part of your antiderivative. It's not like this guy. It never said anything about an a or anything being out there. That 1/3 is not part of your u. Does that make sense? And so I still have it, but then I have the 2x, which is my u. So I need this 2 because the 2x is part of my u. So it's not like it's an extra step like this 1/3 was. This 1/3 was extra because I needed to get rid of my 3. I actually don't need to get rid of my 2. It's all part of the derivative of arcsecant. If you look at the derivative of arcsecant, we have u prime over u, square root of u squared minus a squared. All right, since my u is 2x, I need that 1/2 there. I need that 2x there. It doesn't cancel out like this 1/3 is canceling out. It's a different process. This antiderivative, I am going to just go straight to my arc secant. I'm going to say 1 over a being 3, arc secant of my u, which is 2x, over my a, which is 3, plus c. And so this would be the answer to that guy. I do not have a 1/2 to bring forward. Easy to see at first. So if I were to write this denominator out, right, I would say this is e to the x squared minus 1 squared. Speaking of my properties of exponents, a power to a power, you multiply them. So I have something to a 2x or to a 4x or to a 6x. I can easily write it to a power rate and square it, and that gives it to me, okay? So I can easily see that my function here, my u here, would be e to the x. Du, well, a derivative of e to the x is just e to the x dx. Like, that's simple, right? But I need dx, right? So then what would dx be? Well, if I did dx would equal du over e to the x, right? If I just divided that guy over, right? So far, so good? So if I just divide the ex over, dx is going to be du over e to the x. Well, what was e to the x in my original setup? U, right? So dx is the same thing as du over u. Everybody follow? I just did substitution. So now if I rewrote this whole thing in u, I have du over u, that's my dx, right? I have the square root of u squared minus 1 squared. And now I can see I have arcsecant because I have the derivative of the function in the numerator. On the denominator, I have the function and the square root of the function squared minus a number squared. That is arcsecant. That is the perfect arcsecant, all right? And so now the antiderivative of this is rather easy. I have 1 over my a. Well, my a is just 1 over 1. Arcsecant, right, of my function here being u, and we'll substitute u back in, over my a, which is 1, plus c. If I plug my function in here, my function is e to the x, right? I don't need an absolute value on e to the x because e to the x is always positive. E is 2.17, you know, on infinitely. You'll never make it negative, so you don't even have to include the absolute value. 1 over 1, that's just 1. So you end up with arcsecant of e to the x plus c. Recognizing that as arcsecant is what's difficult, okay? And that's where all of this comes into play. So this one you start to see, you're like, oh, I have a number squared minus a function squared in my denominator. That's going to be arcsine. All right. My problem is I have a function in the numerator, which causes me some issues. Okay. The issue being that I don't have any antiderivative that tells me I can have an x plus 2 up there. However, think back to when my numerator had a higher degree than my denominator, which technically it does, all right, or the same, higher or the same. I have an x squared in the square root, which will give me a degree of 1, and I have a degree of 1 in the numerator, right? Which means I can use division, which means I can split it up, all right? So I can say x over my denominator plus 2 over my denominator, and all of a sudden I have an old u substitution that I've done many times, and then I have an arc trig function antiderivative that I've now recognized. And so we're splitting it up into two pieces here. And so I'm going to say the integration of x over, we'll just say 4 minus x squared to the 1/2, just because that way is easier. And then we have 2 over, and this guy, we can leave this because we're going to recognize him as one of our trigs, our inverse trigs. And so the first one, if I were to do u substitution here, my u would be my 4 minus x squared. My du would be negative 2x dx. I don't need a negative 2x dx. What do I need? I need just an x dx. So this guy's going to be negative 1/2, right? Times the antiderivative of 4 minus x squared to the negative 1/2 dx, right? Make sense? And for this guy here, this is a straight derivative. This is just a chain rule derivative. All right. I add 1 to my exponent, right? And then divide. So I add 1, which would make it 4 minus x squared to the positive 1/2, and then I divide by 1/2, right? That's my antiderivative of him. You add to your exponent and divide by your new exponent. That is just straight up exponential derivatives, antiderivative rules. Add one, divide by your new exponent. For this second piece of it, so now we're going to move to this guy right here. All right, I have a number squared. So this is 2 squared minus a function squared. My function's derivative is just 1, so I don't even have to worry about anything as far as, putting the negative or anything up there. Like, it's straight up just derivative of x is just 1. So this is a perfect arc sine, right? I have a 2 that's being multiplied by it, so I'm going to have a 2 that comes out, right? But then it's just an arc sine. Arc sine of my function is x, over my a, which is just 2, right? And then, of course, we have our plus c added to the end here. So if we simplify this whole thing, this simplifies, the 1/2s cancel, right? To 1. So I have -1. And then we can rewrite it as square root, which I think is what they did. Square root of 4 minus x squared. That's just that to the 1/2. Plus 2 arc sine of x over 2 plus c. And that is my antiderivative. On the right-hand side, this is an arc trig. This is an inverse trig function. Because I don't have an x up here. If I had an x up here, this would also be u substitution, right? Just straight up u substitution, but I don't. So this is a trig function. A squared, my a being 2 squared, minus x squared, my u being x, right? So a squared minus u squared in the root. That is sine, that's arc sine. This 2 is just like if it was on the outside, right? The 2 is just being multiplied. We don't have to worry about him at all. Since my x is just x squared, my derivative of x is just 1. So I don't even have to worry about, had this been 4x squared, I would have said, oh, there's going to be a 2 in my derivative that I need to worry about, right? But I don't. I don't have to worry about anything because it's just x squared. So I have the 2 on the outside. This is a perfect arc sine. My arc sine says I have a number squared minus a function squared. My antiderivative is arc sine of the function x over the number 2. And then, of course, I have the plus c because it's indefinite. From this point to get my answer, the only thing I did was simplify algebraically. 1/2 over 1/2 cancels, okay? Those cancel each other. I'm left with just the -1. I just rewrote it. Instead of to the 1/2, I rewrote it as a square root. So -1 times the square root of this guy plus my antiderivative of that piece plus my c. Quickly and we'll be done. So your a is 1. Your function is 2x, right? Your u is 2x. I do have a 2x there. So when I take the derivative of 2x, I would have a 2, which means I need a 1/2 out there. 1/2. And this 3 you can pull out as well. So you basically out here just have 3/2, right? Dx, that's my derivative, over my a squared minus my u squared. That is a perfect arc sine, right? And so I have my 3/2 times my arc sine of my function, right, which is 2x, over my a, 1, plus c. And of course, this guy you don't have to leave like that. So you can just say 3/2 arc sine of 2x plus c. For this one, you're going to look that you have 3 squared here and x squared here. The derivative of the x is just 1, so you don't have to worry about that at all. The 5 is just being multiplied, so it's also going to be multiplied to your derivative. So you can think of the 5 as out in front here or just being multiplied by the antiderivative. When you have a squared minus u squared, a squared minus a function squared, it's an arc sine, right? And so we just take that 5 and put it in front 5 times. It's the arc sine. For arc sine, you take the function, which is x, over the a, which is 3, and then don't forget to add your c.
So
For this guy, you want to use your technique to separate it, pretty much. So I want to break this up into 2 different integrals. So I want to say the integral of x over x squared plus 1 minus the integral of 3 over x squared plus 1. And so for this one, I am going to do them individually. So if I look at this guy, if my u, why are you bouncing around? There we go. Stop. If my u is x squared plus 1, my du would be 2x. I don't need a 2x, I need just an x. So I know I'm going to have that 1/2. So I know I'm going to have a 1/2 with this guy. This is something in the denominator to the first power. Anytime you have something in the denominator to the first power, it's a natural log, right? Because if I were to, it's a -1, right? And if I add 1 to it, I get to the 0 power and I'm dividing by 0. So automatically you know your power rule does not work here. So if you have any group, or if it was just 1 over x, anything in the denominator to the first power is going to end up being a natural log problem, unless you can simplify it and it not be a first power, okay? So this one right here is going to end up being that 1/2, because I have to worry about that 2 there. 1/2, the natural log of my denominator here. All right, I've taken care of the 2 from my x squared with the 1/2, and the derivative is going to put it in the denominator. So think of what the derivative of natural log is. The derivative of natural log is the derivative of the inside. So if I were to take this derivative to double check it, the derivative of this would be the derivative of the inside, which is just 2x, over the inside itself, which is x squared plus 1. Well, I have x over x squared, which is why I have this 1/2, which takes care of the 2's, x over x squared plus 1. That's exactly what I had up here. So you can always check it by taking the derivative. Easy enough. All right. So that's that piece of it. The other piece over here, I'm going to look, I have an x squared and I add to it a 1 squared. So if you go back to those 3 inverse trig functions, which one has a number squared plus a function squared? Your arctangent. And so this is a perfect arctangent. My function is just x, so I don't even have to worry about the derivative of it because the derivative of x is just 1, right? So from this, I'm going to subtract, the 3 is just being multiplied. I'm going to subtract that 3, and it's a perfect arctangent. Arctangent, right, of my function, which is x, over my a, which is 1. And then, of course, I have my plus c here. And, of course, to simplify it, you can just take out that 1 over here. So you would have 1/2 the natural log of x squared plus 1, which you don't even really need absolute value there because x squared plus 1 is always going to be positive, but it's fine. Minus 3 arctangent of just x plus c. When we first started this, I said sometimes it'll be obvious that you have something squared plus something squared or minus something squared, and sometimes it won't be obvious. In this case, it's not obvious because I have a trinomial. And there's nothing I can do to take the derivative of this trinomial up until this point that we've done so far. Like, I can't make x squared minus 4x plus 7 the u because I have a 2x minus 4 that's going to be left over. And then if I tried to do, u substitution where you solve for x, even that won't work because I have a trinomial. So the only thing you can do here is try to see if it will work as a completing the square, which it really will always work because you'll have something squared and then you'll have a number. And so think about the process of completing the square, if you have not blocked it from your memory, from like Algebra 2. The point of completing the square is to make a perfect square trinomial. So if you remember a perfect square trinomial, a perfect square trinomial looks something like this, a plus b squared, or a minus b squared. It can be either. And your perfect square is going to be the first number squared plus 2 times the product plus your last number squared, right? And so when you have something like this, you're going to take that center number, the 4, and you're going to cut it in half, 2. And then you're going to square it. And that's going to be this third number here that you need. So we're going to say, I'm going to rewrite this guy on the bottom as x squared minus 4x. Cut that 4 in half and square it. So 4 plus 4. This is a perfect square trinomial. I can write that as x minus 2 quantity squared. It's a perfect square. However, I can't just randomly add 4s, right? If I randomly add 4s, then I've changed my function. So I'm going to randomly add a 4, and then I'm going to also subtract a 4, which means I haven't changed it, right? I added 0. You're going to take your middle number, cut it in half, and then square it. And that's how I decide that I have a plus 4 minus 4. And then, of course, I have a plus 7 already attached to my function. So I added a 4 and subtracted a 4. Doesn't affect my function, okay? And then I can rewrite this guy that I created as an x minus 2 quantity squared. And I can combine my like terms here. Negative 4 plus 7 is a positive 3. And now I have a function squared plus a number squared. Even though it doesn't look like a number. It is, I promise. All right. And so now I'm looking at the antiderivative of u squared plus square root of 3 squared. So my u then is my x minus 2. My a is my square root of 3. And now I have an actual arctangent here, right? Arctangent is the function squared plus the number squared. So I'm just going to do it as an arctangent. My arctangent says that I would have 1 over my a. My a is square root of 3. And then the arctangent of my function, x minus 2, over my a, square root of 3, plus c. If you look at the first one, you have a leading coefficient of a 2. It is hard to do completing the square with a leading coefficient because then you have to consider the first and the middle term when you're doing it. So it's easier just to factor that out. So take the 2 out and then factor this guy, and then you'll just have a number in front of it, which is fine. It's not going to cause a problem. It's just multiplication in your antiderivative. Here, the leading coefficient is technically negative, and for this case, you have an odd number, so you'd end up with a 3/2 and a 9/4, which is fine as well. It's easier to have that leading coefficient positive and 1, a positive 1. So you will want to do some factoring there if you have a leading coefficient. And it just creates basically you would just have a 1/2, like on this one right here, you'd have a 1/2 that would come out because it's in the denominator position. And you just have it come out in front because you literally took it out of everything before you started. And so it's just easier to get it out of there. For this one, you'd have a negative 1 in front of your antiderivative because you pulled it out at the beginning. So if your leading coefficient is anything other than 1, like it was in this example, just pull it out first and then stick it outside of your antiderivative. So they worded this differently. Find the area of the region bounded by the graph of f of x equals 1 over 3x, the square root of 3x minus x squared. And then they said the x-axis and the lines, and they have x equals 3/2 and x equals 9/4, all right? So basically they're giving you a definite integral with 3/2 and 9/4 as your upper and lower bounds, okay? And so when they word it this way, find the area of the region, pay attention to your wording, find the area of the region bounded by the graph of the function, and these lines right here, they're saying do definite integration with upper and lower bounds. So what it looks like in a problem format is this. I'm going to go from 3/2 to 9/4, right? And then I am going to do my integration. All right. Now in this case, when we pull that negative out, it's actually going to help us a little bit. You'll see in just a second. So I am going to do completing the square here with my 3, all right? And so 3 is not quite as pretty. So I'm going to do it over to the side just so you can see what we're doing. We have 3x minus x squared. So I'm going to pull a negative out first. So I'm going to pull this negative out, and I'm going to end up with positive x squared minus 3x, all right? Positive x squared minus 3x, all right? And then I have to do completing the square. So I'm going to have to take a 3, cut it in half, and square it. So what happens when I take 3 and I cut it in half and I square it? So 3, cut it in half, and square it. 9/4, right? Yes? Possibly? Okay. So I have negative x squared minus 3x plus 9/4 minus 9/4. Okay? Now, if I distribute that negative through, just pay attention to what I'm doing here so you can see why this works, all right? I distribute it through here in front of that group, and I distribute it through to the 9/4, okay? So I end up with a positive 9/4 and a negative group. Okay? And then I'm going to rewrite these. So I'm going to rewrite them as squares. So 9/4 is the square of 3/2. So that's 3/2 squared. Okay? X minus 3x plus 9/4 is x minus 3/2 squared. I just did completing the square. Completing the square is always going to be your x plus or minus what you cut in half. That little guy up here. It's always going to be this guy right here. That's how completing the square works. Okay? So I just simplified this denominator to look like this right down here. And so I'm going to rewrite it. I'm going to say, okay, I'm going from 3/2 to 9/4. 1 over the square root of 3/2 squared minus x minus 3/2 squared. If you look back at your arc sign, you have 1 over the square root of a squared minus u squared, right? A is my 3/2, u is my x minus 3/2. Okay? So I am going to do my arc sign. My arc sign says that I take my function, which is my x minus 3/2, that's my numerator, and I put it over my a, which is just 3/2. And I'm doing that going from 3/2 to 9/4. My last step here is literally just to plug it in. I'm plugging in my top boundary and subtracting it from my bottom boundary, right? So I'm going to plug in a 9/4, right? minus 3/2 over 3/2. So I'll say the arc sine of 9/4 minus 3/2 over 3/2 minus the arc sine of 3/2 minus 3/2 over 3/2. And if you calculate it out, this little guy is 9/4 minus 6/4, right? Is 3/4 over 3/2. So you'll have the arc sine. The arc sine of 1/2. And 3/2 minus 3/2 is 0. 0 divided anything is just 0. Right? Arc sine of 1/2, right? That's 30-degree angle. So that's pi over 6. Pi over 6 gives you a sine of 1/2. So we have pi over 6. Sine of 0, 0 degrees gives you 0 degrees and 0 radians gives you a 0 sine. It's right here on your, so we have 0. So your final answer here is pi over 6. Your calculator and do all that. They rounded to 3 decimal places. So they rounded there when they put that into their calculator. So the first thing we're going to do is we're going to manipulate our denominator to be a perfect square trinomial. So we're going to take the x squared plus 4x plus 13. We are going to look at the 4. Take the 4, cut it in half. So that gives us 2 and square it, which is what we're going to add to it. So we're going to say x squared plus 4x plus 4. That's my perfect square. And then we're going to we're going to subtract a 4. And then we still have our 13. And so we rewrite this as x plus 2 quantity squared. And then minus 4 and positive 13 gives us a 9. All right, and so that's how I'm rewriting my denominator here. So I'm going to go from negative 2 to positive 2 of dx over x plus 2 squared plus, and my 9 is 3 squared. Okay, and this is a perfect what? Yeah, arctangent. So if I have one function, by the way, if you have it without a square root, you're likely going to use tangent, right? So your sine has a root and your secant has a root and a function on the outside. So one function squared plus the other, plus the a squared is going to give us our arctangent. And so for arctangent, we have 1 over, change colors, there we go, 1 over our a, which is 3, arctangent, right, of our function, which is x plus 2. And if I took my derivative of my function, I would get a 1. So there's nothing within my function that's going to have to be taken out, okay? X plus 2 over my 3. And then that is from negative 2 to positive 2. So arctangent of 0 actually will give you one that you can do, but arctangent of 4/3 is where you're going to throw a wrench in it. So if I do plug it in, I'll say 1/3, and I just left it on the outside when I did it. 1/3 arctangent, and I plug in my 2. 2 plus 2 is 4, so arctangent of 4/3, minus the arctangent. Negative 2 plus 2 is 0, over 3 is just 0. Arctangent of 0 is 0, because that's what gives you a sine of 0, 0 over 1. So arctangent of 0 is just 0. So in your calculator, you need to plug in the arctangent of 4/3 divided by 3. That's your 1/3. And you should get 0.30909 when you do that. This is on page 391. All this does is this breaks down pretty much every function we've ever covered.